Welcome to EDU World Space.
So a right triangle ABC is given. We're given angle A. We have some angle theta here. We're given the length of the side AC. It's equal to B. And then we draw CD, this perpendicular line, to AB. That's why we have this right angle here. And then we go ahead and draw DE so that it's perpendicular to BC. That's why we have the right angle. And we would just continue this process. For example, after this point, we would go perpendicularly to AB, and then we would meet at some point F, and we would just continue this process forever. This will happen infinitely many often. The process is continued indefinitely in the figure shown below. Find the total length of the perpendiculars CD, DE, basically all these lines here. Not the original AC, that's not included. Only the red lines are what we're adding. So let's just find the pattern here. We'll see that eventually that this is geometric. So CD, well, this is a right triangle over here. This ADC, this is a right triangle. So you could use your right triangle trigonometry here to see that, well, we have sine theta equals the red line, which is CD. Let's just over B, opposite over hypotenuse. So I can rewrite this by solving for CD. I get B sine theta. So this largest red line here, CD, is equal to B sine theta. And that's what we want. We want to first express all of these red lines in terms of B and theta, and then we'll come back and add a sum. So first, we're just trying to see what kind of sum it is. So let's go ahead and find a few of these red lines. The next one would be DE. So this time, you're looking at the triangle DEC. So triangle DEC. This is another right triangle. And if this angle was theta, so go back to triangle ADC. This was angle theta. That's a 90-degree angle. That means this angle here is 90 minus theta, but that must mean that this angle down here is theta. So we have another right triangle in here. We have our theta, so we can go ahead and say that the sine of theta is equal to CD, the length CD, over the length DE. Just using definition of sine, the sine is the opposite over hypotenuse. So that's DE over the hypotenuse. And here I made one mistake there. I'm sorry about that. So let me take a step back here. I have the order incorrect. This should be DE over CD. Because again, opposite over hypotenuse. So solve this for DE. And we get that it's equal to CD sine theta. But then using the previous part, this is B sine squared theta. And we'll eventually see that this is the pattern. Each time we find a progression. So the next one would be EF. This one will be sine theta times DE. So this one will be B sine cubed theta. So then this infinite sum here that we're being asked to compute, that's just equal to B sine theta, B sine squared theta, B sine cubed theta, and so on. And this is a geometric series because we're multiplying by the same term each time, which is sine theta. And we know that this sine satisfies the inequality that is between less than 1 and 1. So we know sometimes sine can be -1, sine can be 1, but based on this picture here, we are assuming that this is not 90 degrees. So here, this is angle between 0 and pi over 2. And we know if this is our assumption, that the sine will just be between 0 and 1. So this will converge. And then final answer is to use the formula for the convergent geometric series. It's the first term of the series, and then you just divide by 1 minus r. So in our problem, the first term is b sine theta. We can see that that was the length of the first term, the first side, the longest one over here. And then we just divide by r, 1 minus r, and we just said r was sine theta, so 1 minus sine theta, and that's our final answer. That's the sum of the length of the perpendiculars.